This lesson is about determinants of matrices. The determinant of a square matrix A, denoted A with vertical bars surrounding it, which resemble the absolute value, is a number associated with a matrix that can determine what type of solutions the corresponding system of equations will have. Determinants only exist for square matrices, which is a matrix that has the same number of rows and columns. The calculation of a determinant is different depending on whether you have a 2x2 matrix, a 3x3 matrix, or larger. We will learn how to calculate the determinant of a 2x2 matrix. Then we will briefly describe how to calculate a determinant of a 3x3 matrix. Finally, we will learn how the calculator can assist us in the calculation of determinants in order to allow us to work more efficiently. Beginning with determinants of 2x2 matrices. The determinant of a 2x2 matrix can be calculated using the following formula. Notice the notation for the matrix. We have the vertical bars surrounding the values in matrix form, A, B, C, D, and the determinant is found by taking A times D minus B times C. So for example, let's calculate the determinant of the following matrices. Starting with matrix A, I have the values 2, 3, 5, 9. So we basically cross multiply. So for instance, I start off taking 2 times 9 to begin with, so 2 times 9. Then I subtract the product 3 times 5. So this becomes 2 times 9, which is 18, minus 3 times 5, which is 15. So the result is 3. So the determinant of this matrix is 3. And we'll look later on as to what that precisely means. Let's take a look at another example. So for matrix B, I have negative 4, 10, 1, and 3. So I would take negative 4 times 3 minus 10 times 1. So this is going to be negative 12 minus 10, which is negative 22. So the value of this matrix, the determinant of this matrix, is negative 22. All right, one last example. 7, 21, 2, and 6. So I would multiply 7 times 6 to begin with, and subtract the product 21 times 2. So this would be 42 minus 42, which equals 0. And that's all there is to calculating the determinant of a 2x2 matrix. Let's see how that might be useful. So a consistent linear system, a system that has a single solution, has a determinant that is non-zero. An inconsistent system, a system that has no solution or infinitely many solutions, has a determinant that's equal to 0. So let's take a look at a system of equations. Now, the corresponding matrix, if we change this into matrix form like we did using the Gauss-Jordan method, the corresponding matrix would look like, oops, that's a 3 in the first position. So 3, negative 2, and then 5, 1, negative 1, and 3. So this is a square matrix. And because it's a square matrix, we can't come up with the determinant of it. The determinant is only defined for square matrices. But that's okay. When it comes to using the determinant to determine what type of solutions we have, whether it's a single solution to the linear system, or whether it's infinitely many or no solution, we only actually have to work with the part involving the variables. So we don't have to worry about the part on the other side of the equals. So we look at the determinant of 3, -2, 1, -1. This determinant, if I multiply 3 times -1, that's going to be -3. Then it's going to be minus the product -2 times 1, so effectively plus 2. So I get -1. And since this is non-zero, since it does not equal 0, that tells me that there is one single solution to this linear system. And if we solve this system, just to show you, we can find what that value is. So I'm going to solve the system. The determinant doesn't have any, it doesn't really tell us what the solution is. It just tells us that a solution exists. So let's find out what the solution is. That we have to use elimination, substitution, Gauss-Jordan, one of those methods for. So I'll just use elimination. So I'll take the first equation as is, multiply the second equation by -3. So I would have -3x plus 3y equals -9. And that means the x's would cancel, and I get y equals -4. Knowing that, I can solve for what x is, just plugging back into either one of the equations. So I'm going to use the second one. So x minus -4 is equal to 3. So this would be x plus 4 is equal to 3, which means I need to subtract 4 from both sides, so that will cancel and leave me with x equals -1. So my solution is -1, -4. If you'll notice, my determinant was -1 and the x value of my solution was -1. That's actually completely coincidental. It's not necessarily going to be the case that the x value of your solution and the determinant would be equal. It just happened to be in this case. Okay, let's do another example. Alright, so, whoops, went too far. There we go. In this situation, first I'm going to look to see what the determinant is. So the value of the determinant, 1, 2, 3, 6, would be 1 times 6 is 6, minus 2 times 3, which is also 6, would be 0. So what that means is there should either be no solution or there should be infinitely many solutions to this system. So let's see which it is. Just by solving, I'll multiply the top equation by -3. So -3x minus 6y equals -18. Then 3x plus 6y equals 1. When I add these together, the x's cancel, the y's cancel, so everything on the left-hand side is 0, equals -17. That's our contradiction, which tells us that there is no solution to this system. So a quick look at the determinant, which is generally not a difficult thing to calculate, especially in a 2x2 matrix, can tell you right off if you're going to have a solution or not without doing any sort of solving. So it can't tell you what the solution is, but it can tell you if one exists or not. Now let's look at determinants of 3x3 matrices. So determinants of 3x3 matrices, there's actually two different formulas that I've seen for this. One is more of a system of calculating, and that's my preferred method. The other is a formula that only works for 3x3. It works fine, but the idea about this this other way of doing it, which is more of a system of how to calculate it, tells you how to do the determinant of a 4x4, 5x5, or even larger. So this system would work for any size matrix and not just 3x3. So that's why I'm introducing it instead. So what you have is what's called a matrix of cofactors. And there's a way of determining this matrix of cofactors, but it actually always works out in a nice pattern. You start with a plus in the upper left-hand corner, and then for whatever size matrix you have, you just invert positive, negative, positive, and you always invert, one to the other. So below this positive is a negative. Next to it would be a positive, and so this is our pattern. No matter what size matrix we're using, 3x3, 4x4, 5x5, and so forth, this is what it would look like, just, inverting positives and negatives. Now, what's important there is in order to calculate, we use what's called a pivot. And you can use any row or column as your pivot row or pivot column. It doesn't really matter. Sometimes there's advantages to using one row over another. As you'll see through the calculation, there would be an advantage here of using the second row or second column because there's a 0 in that, both that row and column. But I'm just going to choose the top row to be my pivot. So what happens is I begin with 6 as a multiplier. And if you check the matrix of cofactors, there's a positive in that particular position, which means I use the 6 as is. If there was a negative, I would just make it a -6. All right, now I cancel out everything in that corresponding row and column, which leaves me with a 2x2 matrix. And I multiply this 6 by the determinant of that 2x2 matrix. Okay? Now, straighten that up a bit. Okay. Then I go to my next pivot. And I can use any row and any column. So I'm just going across the top row. I could go down to the 3 as well. I'm just going to the 2 next because, it's I don't really have a particular reason. I'm just going that direction. But what I do is I cancel out everything in that corresponding row and column. And that leaves me with 4 numbers. And those 4 numbers make up a 2x2 matrix. All right, but the 2 is my pivot. And if you'll notice, in the position where the 2 is in my cofactors is a minus. So that means I'm going to do a -2 because it's positive up here, so I make it negative, times the determinant of the matrix 3, 8 to -5. Okay. Then I go to the next one in my pivot row that I'm using. So it's a -1. I cancel everything out in that particular row and column. The cofactor is a positive, so I don't change the sign on it, so it's still going to be -1 times. Now there's 4 numbers remaining, which makes up a 2x2 matrix, and I'm going to do the determinant of that 2x2 matrix. Okay, and I could have very easily have done any other row or column. There may have been an advantage actually using, say, like the second column, because initially I would have come up with those 4 numbers. The next one would have been 0 as my pivot, which I wouldn't even have to come up with the determinant of that matrix that is left over, because I'm going to multiply it by 0. So there's an advantage in choosing that one. And then finally I would be using the 1. So you can use any row or column, so choose to your advantage. All right, but let me figure out the determinant of this 3 by 3 matrix since we're in the middle of the process here. So it's going to be 6 times, and then when I come up with the determinant of this, it's going to be 0 times -5, which is 0, minus 8. Then it's minus 2 times -15 minus 16. Then it's minus 1 times 3 minus 0. So 6 times -8 minus 2 times -31 minus 3. So -48 plus 62 minus 3. So let's see, this would be -48, say minus 3 would be -51, so it looks like it would be 11. So that's the determinant of this matrix. And you could see by this that it would get to be more difficult if we did a 4 by 4. Our pivot row, the process would be the same. It's just initially the pivot would result in a 3 by 3 matrix. Then we'd have to do the determinant of that 3 by 3, each time. So it would just take a lot more work. It's so much work that generally it's understood that calculators would come to the rescue here. So your calculator can do determinants of matrices, and it can do them very quickly, very easily. So we're going to just see how that's done. So let me bring up the calculator, and here's the process. So first enter your matrix menu, so second and matrix. Slide over to edit. We're going to edit matrix A. Here we need a 3 by 3 matrix. And I just start entering the values. So 6, 2, -1, 3, 0, 8, 2, 1, and -5. So those values are in. Now I just quit out of the matrix editor, but go back into the matrix menu here. But now I want to do some math. And the very first option under that math menu is DET, which stands for determinant. I just have to tell it which matrix I want to do the determinant of, and it will do all the cofactors and all of that stuff for us and just give us the final answer in the end. So that's a much preferred method to getting a determinant than actually calculating it out by hand. And when it comes to the expectations of this course, if you have a 2 by 2 matrix, most of the time it probably is faster to get the determinant of a 2 by 2 matrix by hand rather than typing everything into the calculator and doing it. But if that's the way you want to do it, that's perfectly fine. There will be a couple of problems, however, that it is necessary to calculate the determinant. Now I'll show you what those look like later on. But when it comes to 3 by 3 matrices, the expectation is that you're using the calculator. We'll never give you problems in this class where you would have to use the determinant method by hand for 3 by 3. Later classes, you may have to do that, but not in this particular course. All right, let's go down to the next thing to learn about. This is called Cramer's rule. If a linear system is consistent, meaning that it has a solution, then you can solve the system using determinants. This process is known as Cramer's rule. So suppose you have a system of equations. a1x plus b1y equals c1. a2x plus b2y equals c2. We can define the value d as the determinant of A1, B1, A2, B2. So we just take the coefficients off of the variables x and y, plug them into a matrix, and calculate its determinant. That's going to be the value D. D sub x, what we would do is replace A1 and A2, replace those coefficients with C1 and C2, the numbers on the other side of the equal sign. We replace basically what's in the x column with those numbers. And if we get the determinant of those numbers, we call that D sub x. Similarly, if we replace the numbers in the y column with the numbers on the other side of the equals, C1, C2, we can define D sub y. With those three numbers, the solution to our system, the x-coordinate, is D sub x divided by D, and the y-coordinate is D sub y divided by D. So we can actually solve systems using determinants, but there's a little bit more work involved in using Cramer's rule than what we would have just using elimination. But I want to show you how it would work. So let's do this as an example. So x minus 2y equals 5, 3x minus y equals 5. So we first define D as the determinant of just the coefficients, the matrix of coefficients. So 1, -2, 3, -1. So this is going to be -1 plus 6, which is 5. Okay, then D sub x, we replace the 5 and the 5, the numbers on the other side of the equals, into the x column. So 5 and 5 in the x column, and leave the y column alone. And we solve for a determinant here. So this would be -5 plus 10, which is 5. And then D sub y, we replace the 5 and the 5 in the y column and leave the x column alone and solve for a determinant. So now this would be 5 minus 15, which is -10. So my solution is the x-coordinate. So the x-coordinate is dx over d, so 5 divided by 5. The y-coordinate is d sub y divided by d. So this is 1, -2 is my solution. And what's nice is when you're calculating d initially, if d results in 0, so if this number 5 ended up being 0, then you would either have no solution or you would have infinitely many solutions, because the denominator in the 5 halves and the -10/5 would be 0, and you can't divide by 0. So that is Cramer's rule. Another application is finding the area of a triangle. So you can use determinants to find the area of a triangle in the plane formed by 3 points. So the formula is the area is equal to 1/2 times the determinant of the 3 by 3 matrix x1, y1, and the number 1, x2, y2, and the number 1, x3, y3, and the number 1. Which, for instance, if you just had some triangle in the plane formed by 3 numbers, and you created this matrix, did the calculation through the formula, that would give you the area of that triangle that's enclosed. So let's see how it works. Let's find the area of the triangle enclosed by the points 0, 1, 4, 2, and 1, 5. So that area is going to be 1/2 times the determinant of the matrix 0, 1, 1, 4, 2, 1, and 1, 5, 1. Now, as I mentioned, we wouldn't use the process of doing a 3x3 matrix, outright. We'll just use the calculator. So I'm going to go in to my matrix editor, edit matrix A to reflect these values. So 0, 1, 1, 4, 2, 1, 1, 5, 1, and quit out of here. Now I just want to do the determinant of that matrix, and I get 15. So this is going to be 1/2 times 15, or 15 halves, or 7.5, however you want to look at that. That would be the area of the enclosed triangle. So it's pretty neat that there is a geometric interpretation of determinants as well. In fact, there's actually all kinds of things you can do with determinants. We're really just scratching the surface in this course. One thing we can do is solving equations involving determinants. So for instance, let's say I had an equation like this. So basically, I'm looking for the value of x that this matrix has a determinant that's equal to 4. In order to solve for it, I would need to take 5 times x, which would be 5x, minus 3 times 2, which is 6, and set that equal to 4. And now I have a linear equation. So 5x is equal to 10, because I'm going to add 6 to both sides, divide by 5, so that I come up with x is equal to 2. So if I replaced 2 into this matrix, I would get a determinant that's equal to 4. So 2, 3, 2, 5. Let's see what happens. So 2 times 5 is 10, minus 3 times 2 results in 4. So it checks out. Okay. Got another one here. So this one's a little bit more advanced, but is actually kind of showing you a way that these types of equations are actually used in later courses. So I have the matrix 3 minus x, 4, 5, and x equal to negative 38. So let's see what happens. I would need to multiply 3 minus x times x minus 4 times 5, which is 20, and that's equal to negative 38. When I distribute the x into these parentheses, I'm going to have 3x minus x squared, and then minus 20 equals negative 38. Now this time I have a quadratic, and since it's quadratic, I need to get everything to one side of the equation and get ready to factor. So let's begin that process. So if I move everything to the right hand side of the equation, I'm going to have 0 equals, I'll write it, x squared minus 3x, oops, minus 3x that is, and I'm going to add 20 to both sides to move it, so negative 38 plus 20 would be minus 18. Now, I have a quadratic that I believe will factor, so let's try that out. So 6 and 3, that's minus 6 and plus 3, so it looks like x could equal 6 or x could equal negative 3. So either one of these values would result in a determinant that would be equal to negative 38. So just a preview of something that you may see later on in a later math course. But that's all for right now in terms of determinants.